Welcome to Fun Facts Online. Today, we are going to dismantle a fundamental belief about the solid world. If you look at a diamond, a grain of salt, or a piece of steel, your intuition tells you that it is rigid. At the atomic level, we picture atoms locked in a grid, vibrating in place like nervous passengers on a crowded train, but ultimately stuck in their assigned seats. This static, geometric view of solids has been the bedrock of materials science for a century, but in the last few years, and specifically through breakthroughs in 2024 and 2025, that image has shattered. In the ultra-cold, atomically flat landscapes of 2D materials, physicists have found a ghost in the machine. It turns out that when you stack and twist layers of atoms, the pattern they create isn't just a picture. It is alive. It breathes. It shivers. We have discovered a collective, phantom-like vibration called the Moiré Phasons. This isn't just a new particle, it is a new way for matter to behave, a solid that acts like a fluid, allowing layers to slide and undulate even at temperatures near absolute zero. Today we are doing a deep dive into the Moiré Phasons, the discovery that is rewriting the rules of quantum mechanics and could define the future of computing. To understand why this is such a shock to the system, we first need to look at the canvas where this is happening, the field of Twistronics. For nearly a decade, this has been the hottest topic in condensed matter physics. The recipe sounds simple. You take a sheet of graphene, which is carbon atoms arranged in a honeycomb lattice, and you place another sheet on top of it. If you line them up perfectly, nothing special happens. But if you rotate the top sheet by a tiny angle, say 1.1 degrees, the so-called magic angle, the universe changes. The misalignment between the two grids creates a larger, periodic interference pattern known as a Moiré superlattice. You have likely seen this effect in the macro world. If you look through two window screens that are slightly offset, you see a shimmering larger pattern that seems to move as you tilt your head. That is a Moiré pattern. In physics, these twisted cathedrals of atoms have been magical. They have given us superconductivity, strange magnetism, and light that behaves like matter. But until recently, physicists made a simplifying assumption. They treated the Moiré pattern as a rigid stage. We assumed the atoms were locked in a static geometric dance. We were wrong. The atoms are not glued together, they are held by weak van der Waals forces, which means they can slide. And that sliding is where the ghost lives. This brings us to the star of our show, the Phasons. To understand a Phason, you have to unlearn what you know about crystal vibrations. In a normal crystal, like quartz, atoms vibrate around fixed points. We call those vibrations phonons. Phonons are the particles of sound and heat. Think of them like plucking a tight guitar string. It takes energy to pluck it, and it snaps back. It is stiff. A Phason is completely different. It arises because the Moiré pattern is not a physical object in the same way the atoms are. It is a relationship between the layers. Imagine the Moiré pattern is a projected image on a wall. If you shift the atomic layer by a tiny fraction of a nanometer, the projected Moiré pattern shifts by a massive amount, sometimes nanometers or more. This immense amplification means the pattern is incredibly sensitive. In physics terms, we call Phasons massless, or ultrasoft modes. Unlike that stiff guitar string, a Phason is like a loose, floating silk ribbon. It takes almost zero energy to excite it. This softness is critical. It means that even at temperatures close to absolute zero, where all other thermal motion, the phonons, should freeze and die out, the Phasons are still alive. The atoms are still shivering. This creates a bizarre state of matter. Theoretical models, specifically something called the Frenkel-Kontarova model, describe this as a soliton network. The material wants to relax into perfect alignment, so it forms large islands, where the atoms lock together, separated by thin, stressed boundaries called domain walls or solitons. The Phason is the vibration of this entire web. It is the domain walls breathing, flexing, and sliding. It is essentially a structural fluid existing inside a solid material. For years, this was just a mathematical prediction. It was a nuisance term in an equation that suggested the lattice wasn't quite stable. But you cannot build a new generation of electronics on a nuisance term. You need proof. That proof arrived in 2025. Thanks to a team including Yichao Zhang at the University of Maryland and collaborators at Lawrence Berkeley National Laboratory. They did the impossible. They photographed the shiver. This is much harder than it sounds. You cannot just use a normal microscope to see a Phason because it is too fast and too small. It is a blur on top of a blur. To catch it, the team utilized a technique called electron tachography. Traditional electron microscopy works a bit like a shadow puppet show. You blast a sample with electrons and see what gets blocked. Tachography is different. It shoots a focused beam and records the complex interference pattern of the scattered electrons. Then, a supercomputer takes that data and reconstructs the image, correcting for lens aberrations mathematically. This allows for sub-picometer resolution. That is smaller than the vibration of a single atom. When they turned this eye onto twisted tungsten diselenide, they didn't see sharp atoms. They saw atoms that looked smeared. But this wasn't bad focus. It was the phason. The atoms were physically surfing on the Moiré waves. Crucially, the blurring wasn't random. If it were just heat, everything would be fuzzy. But this was collective. The atoms in the domain walls, those stressed boundaries, were vibrating much more intensely than the atoms in the aligned regions. They had captured the first direct visual evidence of the Moiré Phasons, dominating the behavior of a material. They proved that at low angles, the solid material behaves mechanically, more like a viscous fluid or a glass. This discovery changes everything, because in the quantum world, everything is connected. If the stage is shaking, the actors have to move differently. The discovery has immediately solved two major mysteries, one regarding excitons and one regarding strange metals. Let's start with excitons. An exciton is a quasi-particle formed when an electron binds to a hole, a spot where an electron is missing. These are critical for things like solar panels and lasers. In twisted materials, theory predicted that excitons should get trapped. The Moiré pattern creates hills and valleys of energy, and we thought the excitons would roll into the valleys and get stuck, like marbles in an egg carton. But experiments kept showing them moving. They were flowing when they should have been frozen. The phason explains why. The Moiré potential isn't a static egg carton. It is a rolling ocean surface. The phasons create waves in the landscape. The excitons aren't getting stuck. They are surfing these phason waves. This is known as phason-assisted transport, and it means we can move energy and quantum information through a material even when it theoretically should be trapped. The second mystery is the strange metal. Twisted bilayer graphene is famous for becoming a superconductor, conducting electricity with zero resistance. But just above that superconducting temperature, it behaves as a strange metal, where electrical resistance scales linearly with temperature. In standard physics, resistance usually scales with the square of temperature, or in other complex ways. A linear scale is weird. It implies something is scattering the electrons with incredible efficiency, even at low energy. The phason provides the missing link. Because phasons are ultra-soft, remember the loose silk ribbon analogy, and because their coupling strength increases with their wavelength, they can scatter electrons efficiently even at tiny energies. The electrons are colliding with the shivers of the lattice itself. This confirms that the phason isn't just a curiosity, it is the dominant factor in the electronic performance of these materials. So, where do we go from here? We are entering the era of phason engineering. Now that we know the ghost is there, we can try to control it. The implications for technology are staggering. First, consider nano-optomechanics and quantum sensing. Phasons couple mechanical motion to light. By designing twisted cavities that trap both light and phasons, we could create sensors of unprecedented sensitivity. Imagine a sensor that detects changes in gravity or electric fields by measuring how they disturb the collective atomic shiver. Because the Moiré pattern amplifies atomic displacements by 100 or 1,000 times, these phason sensors could be orders of magnitude more sensitive than the micro-electromechanical systems in your phone today. Then there is the holy grail, heat management. Heat is the enemy of computing. In normal chips, heat is carried by random, incoherent vibrations called phonons. It's noise. Phasons, however, are coherent. The 2025 studies suggest that because phasons dominate thermal transport in twisted layers, we could tune the heat conductivity of a material just by twisting it. Imagine a thermal transistor, a material that conducts heat efficiently in one state when the phasons are aligned, and blocks it completely in another. This could lead to self-cooling quantum processors, solving one of the biggest bottlenecks in high-performance computing. Finally, there is qubit protection. Quantum computers suffer from decoherence, the loss of information due to environmental noise. Phasons might be the ultimate shield. By engineering the Moiré spectrum, we could create quiet zones or band gaps in the vibrational spectrum where no heat waves can exist. Placing a qubit inside such a phason bandgap would isolate it from the mechanical environment, potentially extending the lifespan of quantum calculations significantly. The discovery of Moiré Phasons teaches us a humbling lesson. Even in the hardest, coldest crystals, there is motion. Matter is never truly still. By twisting two sheets of atoms, we didn't just create a new pattern, we summoned a new fundamental behavior of matter. We created a solid that shivers like a liquid. We found a ghost in the machine that can carry electrons, scatter heat, and maybe one day carry the calculations of a quantum computer. The static picture of the atomic world is dead. Long live the shivering, sliding, surfing world of the Moiré Phasons. Thanks for listening to G Fun Facts Online.